Today's Quik-Tech-Talk is about converting data into information and then uncovering hidden insights and getting ready to take actions. In the process, we strive to minimize risks. For anything you will see in the following minutes, this is the driving force behind. After the mainframes, microcomputers appeared on the stage. First databases were mostly local because network technology was new. Then they got networked and multi-user databases became common. But storage was still a bottleneck because storage technology was still expensive. As cheaper storage became available, combining data from all those databases into large data warehouses became feasible. For fast and rich analytics, though, large memory is essential, and memory technology was lagging this time. Pre-processing data and storing intermediate results was a temporary solution. Data warehouses were augmented with data cubes for a while. Then, computers with larger memories became affordable. BI really took off with in-memory processing. However, descriptive exploratory analytics, which is the outcome of BI in general, was only able to answer so many questions. Demand for predictive and prescriptive analytics was huge. But compute power was the bottleneck this time. AI requires crunching massive amounts of data, so multi-core CPUs and distributed compute clusters were the solution then. With that solution, AI took off. Let's overlay data maturity onto this. Can we consider any of these levels as less important? On the contrary, each level is crucial to reach the next one. A lot of organizations today, trying to skip a level, never go beyond POC stage to production. Mark Twain, one of the greatest humorists, once said, "History never repeats itself, but it does often rhyme." When I look at these two pictures, I can see the rhyme all right. There are 7 decades between them. ENIAC is the first programmable, electronic, general-purpose digital computer. It was completed in 1945. Here is a fun fact. The programmers of the ENIAC were 6 women. It had to be programmed mechanically with manual resetting of plugs and switches. That's what she's doing in the picture on the left. IBM Q, on the other hand, is IBM's commercially available quantum computer for business and science today. I think quantum computing adds a new level to our maturity scale. Until I hear a better name, I'll call it super optimized maturity level. Predictive analytics today can predict a lot of events: weather, stock market, equipment life cycle, drug interactions in human body. But a black swan event occasionally neutralizes all the gains from these predictions. For example, a stock market crash can wipe out a lot of wealth accumulated over years. Quantum computing, in theory, can deal with even some of these black swan events. To me, that's why it's a big deal, among many other applications it might have. That picture is from a lab. However, this picture is from IBM's latest quantum computing data center. Inside each of those white cylinders, there is a quantum computer, identical to the one those 2 scientists are working on. White cylinders isolate them from the environment, so they stay cool and operate properly. Big black boxes you see in the background, they are just classical computers handling network connections, storage, and so on. Each IBM Q in that data center can be dedicated to a client, like private cloud operations of today. Or, and this is where quantum computing's real power comes out, using quantum entanglement, quantum computers in those white cylinders can act as a single large quantum computer, The entire data center becomes a single large quantum computer or acts like one. This way, they can collectively simulate very complex problems. Complex problems even today's supercomputers need way too much time to solve. After ENIAC, mainframes were built. Then microcomputers replaced them mostly, which led to data centers. Then there has been some consolidation, which is natural and should be expected maybe. But now the cycle seems to be resetting. So when will quantum computing take off? Well, scientific progress is often nonlinear, as we all know. Sometimes it stagnates or seems to stagnate for lengthy periods and then suddenly it leaps forward. Solving current challenges of quantum computing can take years or months. No one knows really. Yet we might as well keep a close eye and stay engaged.